Hey guys, due to today's very exciting Zoom bombing session and the fact that your teacher neglected to put a password on our Zoom meeting, I now have to re-record this lecture on periodic trends. So here we go one more time. And don't worry, now my Zoom meetings all have passwords and waiting rooms as an extra measure of precaution. So hopefully none of you are too traumatized, although I have to say that I kind of am. All right, so what we talked about today in class was the fact that periodic trends are patterns or properties on the periodic table that change in a predictable way. Okay, so periodic trends are properties of elements that change in a predictable way. Now, we saw this before this nightmare of 2020 started. When we were in class, we actually did that activity with the alien organizer or the periodic trends cards that we used to look at how things change. So, like, for example, when we looked down a group of the aliens, they increased in hair length. Or when we looked across a period, they got more fingers. Or, for example, if you were doing the periodic cards, when you went down a group, their top number was increasing in a predictable way. And when you went across the period, the bottom number or the number of notches was increasing in a predictable way. So think back to that activity that we did in class, because that was really was meant to get you thinking about, well, like, how do the properties of these elements change in a predictable way? And what you guys saw yesterday during the demo is that when we looked at lithium and sodium and potassium, and then hopefully you went on to watch the videos of rubidium and cesium, you saw that when we went down this group on the periodic table, oh my God, that was a really bad line. When we went down this group on the periodic table, the alkali metals, we saw an increase in reactivity. They got more reactive. And the question we want to ask ourselves today is, well, why? Like, why do they become increasingly more reactive as we go down a group? So we're going to learn about that trend going down groups, and we're also going to learn at how trends change going across the periodic table as well. So to start off that conversation, we need a couple of definitions. So I'm going to start off over here on the side with a definition of atomic radius. And if you were explaining this to like your fourth grade brother or whatever, you would call the size of the atom. Like, how big is the atom? But because you guys know more than a third grader, you would say that the size of the atom really is the distance from the nucleus to the outermost electron. And remember that outermost electron exists in what we call the valence shell. And we know that the valence shell is the one with the highest principal quantum number, like the biggest coefficient if we were looking at an electron configuration. Okay, so the atomic radius is the size of the atom, the distance from the nucleus from the protons to the outermost electron. Okay, so that's what atomic radius is. Now on the periodic table, we want to look at how does radius change when we go down a group and across a period. So we want to ask ourselves over here, when we go down this group, just like we were talking about in the demo yesterday, when we go down a group and we got an increase in reactivity, what's going to happen to radius? And I guess I'll spoil the surprise, and I'll tell you that we also, when we go down a group, get an increase in radius. Okay, so when we go down a group, the atoms get bigger. In fact, maybe I'll erase my little blue circles here when we're talking about reactivity. And I'm just going to draw, and you guys can draw this too on your notes in your packet on the little periodic tables I've given you to sketch out these trends. You can draw that the radii start off small and they get progressively bigger as we go down the periodic table. Okay, so francium is actually the biggest atom on the periodic table. And we'll talk about why over on the other side, right? Small, and they're going to get progressively bigger. Here's why. Go ahead and pause wherever you guys need to in order to complete your notes. Okay, as we go down a group on the periodic table, down a group, there is an increase in energy levels. For example, if I was looking at hydrogen, hydrogen's electron configuration is 1s1. But if I go down to lithium, the electron configuration is 1s2, 2s1. And if I go down from lithium to sodium, I get 1s2, 2s2, 2p6, 3s1. You guys see how we're getting progressively bigger from a 1s orbital to a 2s orbital to a 3s orbital? Remember, those are orbitals, if we think back to what we learned last week about electron configurations. The 1s is small, the 2s is even bigger. The 2p orbitals are the same size as the 2s, but the 3s is even bigger and even farther from the nucleus. You guys sound so good this time. Okay, so as we go down a group with this increase in our principal quantum number, or our coefficients here, these orbitals are getting progressively larger. Down a group, radius gets bigger. Let's see, down a group, there's an increase in energy level, and thus an increase in radius. It's so awesome how electron configurations can really tell us everything. Okay, now, next, we want to look at the trend across a period. So like what happens when we go from left to right? Does radius change in a predictable way? I just wrote spheroid. Oh boy, you guys, it's late. That crashing of my Zoom session really did it on wrong. Period. Okay, across the period. So let's look across the period. If I'm comparing, like, let's say, sodium to magnesium to aluminum, like if I'm going this way across the periodic table, and it doesn't have to be the third period. Okay, so one, two, period three. Oh my god, I didn't even turn off my phone. You guys, this is a disaster. Okay. Oh shoot, I have to answer that. I'm gonna pause this recording. See what happens here. All right, you guys, I'll be right back. Although it won't even seem like I'm gone because I'm gonna pause. Oh my gosh, sorry you guys. Even though it wasn't really a break for you. That was Mrs. Bodmer. We talked for like forever and now it's super late at night. And I don't remember what I was talking about. Okay, we were talking about going across a period and what happens to atomic radius. Here we go. Let's look across a period. Let's look from sodium to magnesium to aluminum. You guys see how all three of these elements are in the third energy level? Like the energy level is not changing. When we go down a group, like 1, 2, 3, 4, 5, 6, 7, energy level increases and the radius increases. When we go across the period, we're in the same energy level. So you might think that the size of the radius stays the same because they're all in the third energy level. Turns out they actually get a little bit smaller. So like when we go across periods, radius decreases. Now, the reason for that, pretty simple. Across a period, there is no change in energy level. However, there is an increase in the number of protons in the atom. This increase in the number of protons in the atom pulls the energy level in tighter or smaller. So let's take a look. If we look at sodium, 1s2, 2s2, 2p6, 3s1. This is sodium. 11 protons. Magnesium, 1s2, 2s2, 2p6, 3s2. You see how we're still in the third energy level, you guys? Third energy level? But magnesium has 12 protons. This increase in the number of protons is going to make this 3s a little bit smaller than it was before for sodium, which only had 11 protons. Now, if you keep going, you can keep going down the whole period if you want to. We'll just stop at aluminum. Aluminum has 13 protons. 1s2, 2s2, 2p6, 3s2, 3p1. Still the third energy level, but now 13 protons pulling on it. It's going to get even smaller. So as you can see, as we increase in this number of protons going across a period, we're going to get an increase in pull, and thus the radius is going to get smaller. Now, you might notice that when we go down a period, when we go down a group, there is also an increase in the number of protons. So hydrogen has 1, and lithium has 3, and sodium has 11. We're getting an increase in protons going down a group as well. So you might think that increase in protons going down a group will pull the radius in tighter, just that it does across a period. But it doesn't. And that's because of something called shielding. And when you think about the fact that this 1s has a layer of the 2s beyond it and a layer of the 3s beyond that, these increasing layers of bigger and bigger energy levels around the nucleus prevent those additional protons from pulling that outermost electron in more tightly. So there's this shielding effect that happens down a group that does not make the radius get tighter in the same way that it does across a period. And when you guys take AP Chem next year, we will talk more about that and actually calculate how much the protons can pull on those outermost electrons. Okay, so basically I want you guys, even if you don't understand these electron configurations because you weren't here for that sort of optional week of class, this is such a weird time. Don't worry about it. I just want you to understand that radius gets bigger and radius gets smaller. And hopefully those reasons, even without those electron configurations, sort of, make a little bit of sense to you. So your biggest atom is going to be down here, francium, and your smallest atom is going to be up here, helium. Okay, now let's talk about what happens to radius when atoms gain or lose electrons, when they become what we call ions. So our next definition is ionic radius. And this is simply the size of an ion. And remember, an ion is an atom with charge. So what happens to the size of an atom when it gains and loses electrons? That's what we want to look at next. So the specific types of ions we know already. positive ion and negative ions. These guys have special names that you guys need to know. The positive ions are called cat ions. You can remember that they're called that because the T looks like. And the negative ions are called anions. And in order to understand what happens to the radius, you simply need to think about, well, how does an atom become positively charged? It becomes positively charged by losing valence electrons. Let's look at what would happen to sodium if it lost valence electrons. So remember, we put in this configuration before. 1s2, 2s2, 2p6, 3s1. If this electron were lost, this energy level is now empty. And so now the outermost electron is in the second energy level. That's going to be a smaller radius. So all you guys need to know is that when sodium becomes sodium 1 plus, it becomes smaller because it lost that whole third energy level. That electron is now gone. Where did it go? Well, it probably went to something that wants to gain electrons and become an anion, become negatively charged. So anions gain valence electrons. Let's say we were talking about, I don't know, fluorine. 1s2, 2s2, 2p5. If fluorine became fluorine 1 minus, like let's say we have an atom of fluorine, if it were to gain an electron, it would go right there into that 2p orbital to become 2p6. We haven't changed energy level, right? We're still in the second energy level. So you might predict that this ion is going to be the same size. But remember, electrons repel each other. If we were looking at the orbital diagram here, we would be talking not about 5 valence electrons anymore. Now we would be talking about an additional sphere in that orbital. That's going to cause the electrons to repel each other more than they did before. So the radius is going to get a little bit bigger. So when things get when things get negatively charged, they become slightly bigger. So all I expect you guys to know about ions is that when they're positively charged, they are smaller, and when they're negatively charged, they are bigger. And our next unit is all about ionic bonding. So this idea about what a cation is and its size, and a negative ion is and its size, is going to play an important role in understanding ionic compounds. Okay, so moving on to our second trend. And this trend is going to help us explain why those alkali metals got more weight. And this trend is called ionization energy, often abbreviated simply as I. And this is exactly like its name says. It is the amount of energy needed to remove an electron from an atom. How much energy does it take away an electron? So let's look at the elements that we looked at in the demo that I did for you guys yesterday. 1s2, 2s1, and sodium. 1s2, 2s2, 2p6, 3s1. And potassium was the last one. 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. So the ionization energy, you guys, is the energy needed to remove that electron from lithium, that electron from sodium, and that electron from potassium. And I want you guys to be looking at these electron configurations and also thinking about radius. So remember, when we go down a group, I guess I should have written this one down. Go across, because that makes you think like it's across a period, but really I'm talking down a group, you guys. This radius is getting bigger. How bad is this? I'm going to go ahead and rewrite them like this, so it makes more sense. So that's 2, 2p, 6, 3s, 1. So you don't. And potassium, 2, 2s, 2, 2p, 6, 3s, 2, 3p, 6, 4s, 1. Okay, this makes more sense. I'm sorry you have to listen to this. Oh, I guess I could have paused the recording again. Too late, you guys. You're getting a tired Mrs. Rivera garbage collector after being zoomed on. Okay, here we go. When we go down this group, oh no, no, right with the eraser. When we go down this group, radius is getting bigger, right? Because this is my 2s, and this is my 3s, and this is my 4s, right? So these are representing the valence shell. You guys see how this electron, which is really close to the proton, is going to be a lot harder to remove because it is so closely attracted to those protons and neutrons. This is much harder to remove than this electron. This electron is really far away. This electron is easier to remove because it's farther away from the pull of the proton. So it's all based on radius. You guys understand radius? You can understand ionization energy. When the radius is small, the electrons are harder to remove and require higher ionization energy. You have to put more energy in order to remove that electron. The radius is big. The electrons are far away and they're easier to remove. They require lower ionization energy. Okay, so small radius, hard to remove, high ionization energy. Big radius, easy to remove, low ionization energy. Which means that if you only need a little bit of energy to get that reaction to happen, that reaction is going to be really exciting. It's going to happen really fast. And that's why potassium was the most reactive. Let's go back to our periodic table. Let's draw that trend in. Okay. So when I look down here, as I go down this group with an increase in radius, I'm going to get a decrease. Let me separate these things here for you. Decrease in ionization energy. That's why they were more reactive. It only took a little energy to pluck those ions off of these electrons off of these big radii. When we go across and radius decreases, ionization energy increases. This helium guy, this smallest radius over here, is going to be really hard to pull that electron off. It's going to have the highest ionization energy. So our biggest radius is going to have the lowest amount of energy needed to remove the electron. And I'm going kind of fast, you guys, so go ahead and just pause wherever you need to. And our smallest radius is going to have the highest ionization energy. Okay. So if we wanted to add that sort of statement over here for ionization energy, down a group, ionization energy decreases as electrons are farther away from the protons and thus easy to remove. And then across a period, ionization energy increases as electrons are closest to the nucleus and thus harder to remove. Okay, we've made it. We've made it to our last trend. This last trend is called electronegativity. And again, if you were looking for sort of just like a simple little word to explain this to explain, electronegativity, I like to call love. Oh, I'm even worse at drawing hearts. On here, oh my gosh, I hope you can't hear my family yelling. Being very silly. This is love for electrons. Now that's not really what it is. Okay, so like really electronegativity is the ability, oopsies, sorry, the ability to attract electrons in a shared covalent bond. You know, actually, you guys, I should have said the ability to attract shared electrons, the electrons that are being shared electrons in a covalent bond. Okay. Now, you don't even really know what covalent bonds are yet. That's my next unit. This is going to be important stuff. This is actually what determines whether or not a bond and thus a molecule are polar or nonpolar. I know you remember that from biology, right? Okay. So, if we just think about it as love for electrons, guys, we can very simply explain this using radius. So if I go back here and I look at my periodic table, and I know that radius is getting bigger down in group, ask yourself, how much can the protons in this big, huge atom, can these protons really attract that electron? Like how much do these protons love that electron? Not nearly as much as the protons here in this nucleus, and hydrogen can attract that electron really small. So like when they're far away, they are harder to attract in terms of electrostatic force. I mean, that's probably also true like in nature, by like long distance right? Harder to stay attracted to each other. Sorry for any of those of you that are so if we go down a group and radius is getting bigger, that means there's less love for this electron. So like if an atom can barely even attract one electron, it's definitely not going to attract or pull on a neighboring atom's electron in a bond. Okay, so typically we saw a decrease in ionization energy down a group. We also see a decrease in electronegativity. I abbreviated as E. Is you get a decrease in ionization energy and a decrease in electronegativity because the atom is getting bigger. Okay, so ionization energy and electronegativity are not the same thing. They do have the same trend. Same thing across a period as these atoms get smaller. Although I just drew helium bigger than hydrogen. Is bigger than helium should be small. Sorry, there I go being not great again. So it's that COVID, you guys. I'm not even gonna erase it. You guys understand. What was I even talking about? Ionization energy and electronegativity increases because as these atoms get smaller, there's going to be a stronger and stronger attraction to their own electrons. And if there's a really strong attraction to their own electrons, you bet your butt that there's going to be a really strong attraction to other atoms' electrons. Okay? So let's go ahead and write that out over here. The electronegativity stuff doesn't totally make sense yet. That's okay. We haven't talked about covalent bonding. So it'll make sense when we talk about that. But I just want to introduce it here because it is important. So down a group, there is an increase in electronegativity as radius. I just wrote that completely backwards. Down a group, there is a decrease in electronegativity as radius is larger. Big atoms barely attract or weakly attract their own electrons and thus don't strongly attract electrons in a bond. Their radius is too big. They can't snuggle up close enough to another atom's nucleus in order to attract that other atom's electrons. And that's what a covalent bond is. It's a shared attraction for electrons between two atoms. And so lastly, oh my gosh, you guys, we made it. Across a period, there is an increase in electronegativity as radius is smaller. Because smaller atoms can snuggle up right next to each other and attract each other's electrons. So smaller atoms have a stronger attraction to electrons. Okay, let's go back to our periodic table. One. And make sure we have our electronegativity trend in here correctly. So I've been making a lot of mistakes. So when we go down a group, the radius gets bigger. The electrons are far away, thus they are easier to remove. So you get a decrease in ionization energy, which is the energy needed to remove them. You also get a decrease in electron negativity, or attraction to electrons, because the radius is so big. So francium will also have the lowest electronegativity value. Here's one last little piece of information. You might expect, because helium is the smallest atom with the highest electronegativity value, nope, with the highest ionization energy. You might also think that helium has the highest electronegativity, but it doesn't. In fact, the noble gases don't have electronegativity values at all because the noble gases don't bond. And one of the key parts of my definition for electronegativity was the ability to attract or pull on electrons in a bond. And because the noble gases don't bond, they don't have any electronegativity values. So what's my next smallest atom here that's going to really strongly attract its own electrons and other people's electrons? Not people's, elements. Fluorine is the most electronegative atom on the periodic table. It's going to have a really strong pull on electrons in covalent shared bonds. Which again, the reason why this is important, this was a tough sort of long lecture to go through. The reason why that's important is because it's going to help us determine the behavior of polar and nonpolar molecules. All right, good job, you guys. We made it. We survived our Zoom bombing. We survived our periodic trends lecture. We'll spend the rest of the week just reviewing, having a little fun with some problems, and we just move on to bonding next. Yay, writing names and formulas. You're going to love it. All right, you guys have a good night.